Today we will discuss about nuclear magnetic resonance spectrometry. Like what I was telling about the mass spectrometry, same considerations hold good with respect to nuclear magnetic resonance spectroscopy also. The basic requirement is for the organic chemistry people, and we will take a quick look at the theoretical aspects and a slight inquiry into the instrumentation aspects, but more or less it is the domain of the organic chemists, either for taking the spectra, interpretation and utilization of the spectra. However, for brevity's sake, we will discuss about the nuclear magnetic resonance spectroscopy, and quickly we will run through, and then we will go to electrochemical methods of analysis. So, in nuclear magnetic spectroscopy is a technique for determining the structure of the molecules and ions and for their quantization based on the transitions between the energy levels of the atomic nucleus, not the electrons, nucleus, under certain conditions. The energy involved is in the radio frequency range. Only those nuclei which have got spin on their own axis can give rise to signal in NMR. Even so, NMR is extremely useful because the signal given by a nucleus is influenced by its environment, that is number of protons present, number of other functional groups, atoms, electronic distribution, etc. In other words, the signal from a nucleus gives information about its neighboring atoms, charge status, etc. This often leads to the determination of complete molecular structure. That is where the value of the NMR lies. We can take a look at this figure, and the nuclei of certain isotopes have an intrinsic spinning action around their own axis. The spinning of a charged particle generates a magnetic moment, as we all know, along the axis of the spin. For example, in this figure you can see that this is the nucleus, and this is the x axis, and this is the z axis, and this is the y axis. So, a spinning nucleus generates a magnetic momentum mu along the z axis in the with a magnetic motion like this, and these two I will explain to you later. The if an external magnetic field is applied now, their spin can align with or against the field, and each individual nucleus spins around its axis, and the axis of the nuclear magnetic moment also precesses around the line of the force of the applied magnetic field, like a top shown here in this case. Here I am applying the magnetic field, and this is the nucleus, this is the magnetic field generated. Here it is H 0, and this is here it is the magnetic moment generated here. This is exactly equal to H 0, it is H 0 greater than H 0 dash is greater than H 0, and here it will be less than that. So, you can see that the energy levels are split into different states, that is minus half plus half, with an magnetic moment like this, and here also the lines are split, and if it is magnetic moment is 1 by 2, you get plus or minus half, and if it is 3 by 2 you would end up with 5 lines 2 I plus 1. So, the spinning motion of the nucleus is quantized and it is associated with a spin quantum number I. The relation between the mass atomic number and the spin quantum number is shown in the next table. That is, we have some atoms with mass number even and number of protons also even. So, the number of neutrons must be even. Such elements will have 0 spin quantum number. Examples include 12 carbon, 16 oxygen, 32 sulfur, like that, all are even. And we can have odd mass number and atomic number could be odd and number of neutrons could be even. Such elements will show spin quantum number either 1 by 2 or 3 by 2. Examples include 1H, 19F, 31 phosphorus, 11 boron and 79 boron. Other examples are odd mass number and instead of odd it is even number of protons and odd neutrons. These are also NMR wise they are active elements like 13C and 127 iodine. And then we can have even and odd in this range, and then this also could be odd. That means, both protons and neutrons, if they are odd, it gives you an even mass number, and these are the examples 2 hydrogen and 14. So, nuclei with both A and Z have I is equal to 0 and they do not give NMR signals. So, for a nucleus to be magnetic, it must possess spin angular momentum with a magnitude of h by 2 pi square root of I into I plus 1. So, the maximum observable value of the spin angular momentum is given by h I by 2 pi, where I is the spin quantum number of the nucleus and h is the Planck's constant. It generates a magnetic moment mu parallel to the axis of the spin. Like spin moment, magnetic moment is also quantized. The magnetic quantum number m has the values of minus I plus 1, 0 and I minus 1 and I. So, total is 2 I plus 1. The ratio of the magnetic moment to the angular moment y is known as gyromagnetic ratio. Different nuclei have different gyromagnetic ratios. The maximum observable component of the magnetic moment mu has a value of mu divided by I is equal to frequency into h is equal to 2 pi into I. So, the nuclei with I is equal to half behave like charged spinning spheres and give well resolved spectra. Such nuclei include 1H, 13C, 19F and 31 phosphorus. Among the nuclei with I is equal to 3 by 2, 7 lithium, 11 boron, 35 chlorine are important. Nuclei with integral spins of I is equal to 1 include 2H and 14N that we have seen in the table. Nuclei with spins greater than 1 by 2 behave like non-spherical charged rotating bodies and show line broadening in NMR spectra. Several organic compounds contain only carbon, hydrogen and oxygen. Since 12C and 16 oxygen do not have nuclear magnetic moments, only the proton spectra are usually observed. 13C has a low natural abundance of 1.1% only. That means, it is not observed in ordinary NMR. So, the most of the NMR work is related to the proton NMR. Nowadays, C13 NMR is also gaining lot of prominence and people are using C13 instruments are commercial instruments are available C13 NMR spectrometers. So, the magnetic moment of a spinning nucleus can assume 2I plus 1 orientation as I was telling you with respect to the external magnetic field leading to 2I plus 1 discrete energy levels. So, the energy levels can be calculated using this equation, this I have already told you, where I is the spin quantum number, m is the magnetic quantum number, mu is the magnetic moment of the nucleus and H 0 is the external magnetic field, that is applied magnetic field having a strength of Gauss having the strength in Gauss and E is the energy corresponding to that orientation. So, the allowed values are like this 2I plus 1 and spin with half has got 2 orientation, spin with 3 by 2 has 1 has 3 orientations, etc. So, this is the figure what I was showing you earlier and the moment you see spin orientation and energy levels of nuclei in a magnetic field, you will be seeing the splitting of the magnetic energy levels. This figure I have shown you earlier. So, the transitions between the energy levels produced by the application of the magnetic field can occur according to the selection rule delta m should be changing only by whole numbers, that is plus or minus 1. So, the resonance frequency corresponding to this makes the transitions possible and it is given by delta E is equal to h mu 0 which is also equal to mu into h 0 upon I. So, keeping the magnetic field h 0 constant, if an increasing radio frequency constant is passed through a coil in the YZ plane and RF frequency creates an alternating field in the x direction. So, when H 1 equals the resonance frequency mu 0, the energy is absorbed by the spinning nucleus flipping the spin direction such that its magnetic moment processes against the applied field. This is known as Larmor's frequency. This I have shown you in the first slide, that is this. Here I have the applied field here and the moment the magnetic frequency is matched by the applied field, the spin will be changed in the opposite direction like this. First it was on the top, now it is on the at the bottom. So, this is known as the frequency at which this happens is known as Larmor frequency. So, there is a linear relationship between the resonance frequency of the applied magnetic field H 0. Therefore, we can either keep H 0 as constant and sweep the radio frequency or keep the radio frequency constant and vary the applied magnetic field H 0. Therefore, this gives us two ways of running an NMR spectrometry. So, magnetic field strength usually is expressed in terms of Gauss or Tesla and 1 Tesla corresponds to about 10,000 Gauss. So, for a proton we have the momentum corresponding to 1.41 into 10 raised to minus 30 joules per Gauss inverse or 2.7927 nuclear magnetons. So, if a magnetic field of 14,092 Gauss is applied, then you can calculate the frequency corresponding to the change and you would end up with 60 into 10 raised to 6 seconds inverse. Thus, the resonance frequency of a proton in a magnetic field of 14092 Gauss would be around 60 megahertz. That is what it means. So, you can have a magnet of 14092 Gauss and you should operate it at 60 megahertz to see the NMR spectrum. So, in NMR the strength of the signal is approximately equal to the square of the magnetic field. Strong magnetic fields can be produced using superconductors. So, this is what has spurred the development of NMR, because very strong good magnetic magnets have become available. So, the magnetic resonance properties of selected nuclei I have put them here. This is 1H, 2H, 13C, 19F etcetera. Their magnetic moments are here and relative sensitivity at constant H0 is there. These are all in the multiples of the nuclear magneton, that is Eh by 4 pi mc, and NMR frequency corresponding to that is 60. This is at 14.09 kilojoules, that is 14,960 kilojoules, and this is at 21.14 kilo Gauss. If you apply a magnetic field, the frequency would be, you would be getting is around 90 megahertz. Similarly, at this 23.49 you would get a frequency of about 100. Similarly, you can see that 1H, 2H, 13C etcetera. Here you can see that with respect to 1H, relative sensitivity is 100, whereas for 2H it is only 0.96. Similarly, for 13C it is 1.59 because of the presence of the magnetic the isotope, but the intensity is only about 1.59 compared to 100. So, like that one can calculate what are the different numbers involved. This is the NMR spectrum of different isotopes. Here you can see 1H, assuming that this is around 100, you can see that intensities of the peaks or instrument response is for boron, copper and then sodium etcetera. They are all very small compared to protons, and silicon is slightly better, 2H is very less, and this is the x axis is the magnetic field. So, when there are two allowed energy levels, the distribution of a population of nuclei at equilibrium follows the Boltzmann distribution. What is Boltzmann distribution? It is this part, e raised to minus mu h 0 upon k T, where k is the Boltzmann constant and T is the absolute temperature. So, the distribution in the upper energy state to compare to the lower energy state, that is the ratio is governed by the Boltzmann equation. So, for a proton at 14090 Gauss, the applied magnetic field should be approximately equal to lower and higher populations of the nucleus at lower and higher energy levels. Therefore, it is easy to saturate the whole system. That means, after a very short time there will be no signal, because the number of nuclei absorbing RF energy and flipping over from one to another would become equal, and therefore, the relaxation process that allow nuclei at higher energy state to the lower energy state by different ways are important for the relaxation back to the lower energy state. Therefore, you can see only a constant absorption peak. So, there are two types of relaxation processes. One is spin lattice or longitudinal relaxation, by which the nuclei with higher energy transfers its energy to the lower other nuclei to increase their translational and rotational energy. That means, the one with higher energy can translate its energy to other nuclei, and other nuclei will gain translational or rotational energy. For example, this process is associated with a time constant. It takes some time for the excited nuclei to transfer part of its energy. This is denoted by T1, which is the time required for the ratio n upper to n lower, that is population of the atoms, to reach 50% of its actual value in presence of its the applied magnetic field H 0. The second type of relaxation is the spin-spin transverse relaxation. In this process, the nuclei exchange the spins with neighboring nuclei by interaction of their magnetic moments. So, in this process, the nuclei exchange the spins with the neighboring nuclei by interaction of their magnetic moments. Although no energy is lost by this mechanism, the precessing nuclei lose phase coherence. Some precesses faster and some precess slower. So, the net magnetization in the xy plane falls towards 0. The time constant for this type of relaxation is associated with this process is T2. We will discuss it later. The thing is, for solids and viscous liquids, the first type, that is T1, is of the order of hours, and for liquids and dilute solutions, T1 is in the range of 0.1 to 100 seconds, that is hardly about 1.5 to 2 minutes. In general, T2 is less than or equal to T1, that is translational and rotational energy transfer is always higher than the spin translation. The width of the absorption line, therefore, it is related to T1, because that is the fastest occurring relaxation. It is related to this by the equation delta mu 1 2 is equal to 1 over T1, where delta mu, where mu 1 2 is the line width at half hertz, half height in hertz. If T1 is 1 second, the line width at half the height in the hertz would be 1. So, the conventional NMR spectrometers scan the spectrum slowly to avoid passing very narrow lines too fast. If you scan it very fast, you would miss so many narrow lines which are having very low intensity. So, most of the time is spent on recording the background, and only a small amount of time is utilized for recording the peaks, which contain all the information one looks for. Basically, this leads to low efficiency and low sensitivity. The time required for a scan by the conventional method is given by delta over r, that is where delta is the range of frequencies required to be scanned and r is the resolution desired. So, if you take a look at the magnetic schematic diagram of NMR spectrum, you would see that there is a DC magnet and a supply is there, power supply, and the sample is ensconced in a coil again, and this is an RF oscillator. There are at least 2 or 3 RF oscillators in a given NMR, and all these RF oscillators are tuned to magnetic sweeps and sample around that. And then we have routine amplifiers and comparison circuit and recorder, and this is the NMR sweep, that is one of the RF coil is used for sweeping the NMR from 0 to 60 hertz or something like that. And for a 13C NMR at 25 megahertz, a typical delta of 5 kilohertz and the line width of about 1 hertz, the scan rate has to be 1 hertz per second, and the total time required would be 1 hour 23 minutes. If the spectrum is divided into a number of small frequency intervals, and if all these frequencies are applied simultaneously, the spectrum can be obtained much more quickly. That is, if n is the number of the bandwidths of the signal and S by n ratio improves by a factor of n raised to half. This is known as Felget's advantage. We have discussed about Felget's advantage and other things in the FTIR. Now, the same thing can be applied in the case of magnet NMR, and to obtain the Felget's advantage, this is achieved by Fourier transform NMR. So, for Felget's advantage for a proton is about 30 for 13 carbon atom C 13, it is about 100. Proton is 30 and C 13 is 100. So, in FT-NMR what do we do exactly is we take a strong RF pulse and apply it to the sample in a very short time duration of 1 to 100 seconds. This is applied by means of a coil placed parallel to x axis of the spectrometer. The pulse contains a wide band of frequencies on either side of the center burst, and due to this all the magnetic nuclei are excited simultaneously. So, after the pulse, the processing magnets revert back to their original state, inducing a sinusoidal wave that we have discussed in while discussing FTIR, and a sinusoidal voltage is also obtained, a corresponding one, and it is obtained in a coil surrounding the sample. So, this is the sum of all these NMR signals, and after Fourier transformation the spectrum appears similar to conventional spectrum. So, the NMR spectrum can also be operated using Fourier transform method. So, nuclear magnetic resonance frequencies are to a small degree dependent upon the molecular environment of the nucleus. This point we have to understand very clearly, because it is the protons that we are handling the signal, but the frequency of each proton is dependent on the molecular environment of that proton, particular proton. Since the surrounding electrons shield the nucleus, the effective magnetic field experienced by the nucleus is slightly different from the applied field. Therefore, electronic shielding results in induced circulation of the electrons about the nucleus. These circulations are induced further by the applied field and are in a direction perpendicular to the applied field. That means, you apply the field, but the variation will be in the direction perpendicular to the field. They produce a magnetic field in turn opposing the applied field, and the proportional to the magnitude of the applied field. The first is they produce a magnetic field opposing the magnetic field. Another is it is the signal is proportional to the magnitude of the applied field. So, the effective magnetic field is given by H 0, that is original applied field, minus that shielding effect, that is given by sigma into H 0, where sigma is a small fraction and sigma H 0 is the induced magnetic field. The separations of resonance frequencies of nuclei in different structural environments from some arbitrary standard we have to know, because every electron, every proton experiences different electromagnetic field depending upon the sigma into H 0. Therefore, how do you rate the frequencies, how much each proton is feeling the effect of other protons. So, you need to have a standard, and this is known as arbitrary standard that is known as chemical shift. So, you take an arbitrary standard and from the standard you measure the distance where the peak appears. So, the NMR spectra in which the width of the resonance line is as large or larger than the resonance shifts caused by different chemical environments are known as wide line NMR spectra. These can give information, wide line NMR spectra can give information regarding the concentration and physical environment of the nuclei, but not their chemical environment. So, wide line NMR spectra provide a rapid non-destructive method of quantitative analysis. For example, proton contents of the fats and oils can be measured. You can just calculate how many hydrogen ions are there in a given fat sample or oil sample. Moisture content in a variety of samples can be determined by wide line NMR spectra, because it is a question of determining how many hydrogen atoms are there. So, fluorine in fluorocarbons, that can be determined. The width of the absorption line is related to the motional freedom of the nucleus in the lattice. This gives valuable information also to polymer chemists and solid state physicists also. So, the applications are usually interesting to the chemistry people, medicine people, as well as oil technologists and physicists and polymer chemists. So, we can let us discuss a little bit about the NMR spectrometers. So, continuous wave NMR spectrometers consist of 6 basic parts. One is you need a powerful magnet and you need 2 or 4 RF channels. I had explained to you this earlier. One serves to stabilize the magnetic field or radio frequency, and another provides irradiating energy. Third RF coil may be used for decoupling the nuclei. Then you need a sample probe containing coils for coupling the sample with the RF field. That is also important. That means, the sample also must be having some sort of a coil which can couple with the applied RF field, and a detector you need to process the NMR signals, a sweep generator for either magnetic field or for radio frequency field. You need to sweep the magnetic field or the radio frequency field, and then you need a recorder to display the spectrum. So, these are the basic fundamental machine parts. NMR schematics of the continuous wave NMR include a magnetic control, a magnet, a lock control, transmitter, sample probe, and the magnets have to be applied around the sample, and you need a modulator, phase detector, and then recorder and a sweep mechanism for the sample. So, what type of output you get from NMR is the question. So, here is the C2H5I, that is ethyl iodide high resolution spectrum. You would get something like this, a single peak, and this is a multiplet, and these are the other peaks you would get. This is the integral spectrum, that is the total height of the peaks. For example, the integral in this range corresponds to this peak in general, and integral in this range will correspond to this, and integral here is corresponds to this. So, with these integration data you can calculate how many hydrogens are there with respect to each other on each carbon atom, and this is the reference signal. So, this is how you would see a NMR spectrum, and the magnet should give a very high field strength which is homogeneous and stable. The stronger the magnetic field, the better is the separation of the absorption lines. Also, multiplet overlapping decreases with increasing field strength. If a stronger field is applied, the separation of the energy levels of the nuclei would be greater, and the Boltzmann distribution favors the lower energy level. Therefore, sensitivity also increases, because more number of nucleus are there at the lower energy level. To ensure homogeneity of the magnetic field, two large pole pieces made of the homogeneous material must be put together. In between, the sample must be inserted, so that the sample should experience the magnetic field. So, the pole faces are usually polished, the gap between the poles is kept narrow, slim coils are used for correcting any inhomogeneity, and usually permanent magnets are cheaper than the electromagnets, because permanent magnets are easy to maintain, but they require elaborate shielding and should be thermostated to plus or minus 0.001 degree centigrade. Electromagnets usually require elaborate power supply and cooling system also, but they can be operated at different field strengths just by changing the input. So, commercial NMR spectrometers operate at 14.9, 21.14 or 23.49 kilogauss. Using using superconductivity technology, we can even operate them at 51.7, 70.5, 93.5 and even 117.4 kilogauss fields can be produced, which can provide very high resolution NMR. So, the probe unit, let us discuss the probe unit. The probe unit is basically a sensing element of the spectrometer. It is inserted between the magnetic poles by an adjustable probe holder. It is just a sample holder in which you can insert the sample. So, the probe holder houses the sample holder, RF transmitters, output attenuator, receiver and a phase sensitive detector. The sample holder is basically a thin walled glass tube of about 5 mm outer diameter, and to average minute inhomogeneities, the sample holder also must be rotated during the operation of NMR at around 1200 to 2400 rpm. The sample is filled to get a length to diameter ratio of about 5. That means, you can have either the liquid sample or the solid sample, and there usually a mark is provided in the sample up to which the sample must be filled. So, a few micrograms to a few milligrams of the sample can be dissolved in a solvent like carbon tetrachloride, carbon disulfide or a completely deteriorated chloroform, acetone or benzene. That means, there should not be any hydrogen in the given sample except your sample. The solvent should not have any hydrogen atoms. That is why we choose carbon tetrachloride, carbon disulfide or completely deuterated chloroform, acetone or benzene. The solvent should not contain hydrogen. The magnetic resonance response of the deuterium nuclei is used to lock the ratio of the magnetic field and frequency of the instrument over long periods of time. So, single coil probes as well as dual coil probes are available. Tetramethylsilane, that is this very standard internal standard, is traditionally used as internal standard, but there are other materials also available nowadays. So, minimal type NMR spectrometers are relatively cheap and suitable for proton NMR measurements. Multi-purpose NMR spectrometers are more sophisticated line and they are versatile. They provide high precision and they are used in research. Wide line NMR spectrometers have a permanent or a lightweight electromagnet with large sample tubes, and the sample temperature can be varied from -170 to 200 degree centigrade. So, FTIR NMR is similar to the continuous wave NMR, except that it has a computer controlled pulse generator and a digital computer for signal processing and presentation of the spectra. So, operator skill requirements are much reduced in FT-NMR. So, this is the schematics of the FT-NMR, and you can see that RF oscillator is there, and this is the RF gate which can be opened on and off depending upon the requirement, and it will only when the gate is on, the power amplifier it is fed to the power amplifier and it goes to the probe, and this is there is a D2 lock and then amplifier gate. These two must open simultaneously, and then it goes to a receiver, filter, and whole operation is controlled by the computer, and which the spectrum can be displayed on the oscilloscope. You can have a recorder also automatically. So, in powdered solid samples, molecules are oriented in all possible directions. This results in broadening of the NMR lines. The shielding of any particular nucleus depends upon the electronic environment and the orientation of the molecules in which it is present. This is known as chemical shift anisotropy. This kind of broadening of NMR spectrum can be overcome to a large extent by rotating the sample very rapidly of the order of about more than 2 kilohertz about an axis oriented at an angle of 54.7 degrees. This is known as the magic angle with respect to the applied field. The averaging that occurs is similar to tumbling in liquids, and the angle is a property of the local fields that electrons exert on the nuclei. Another important parameter that NMR spectra provide are chemical shifts, coupling constants, spin lattice and spin-spin relaxation times. The same type of nucleus in different chemical environments experience different kinds of shieldings from the applied field depending upon the distribution of the electronic charge in its surroundings. Every proton must experience different electromagnetic field, and if the external field is held constant, different shielding effects can cause slightly differing resonance frequencies. This is the fundamental principle. So, you would get different kinds of spectra defined by the shielding constant given by H 0 minus sigma H 0. This we have already discussed, but what is more important is the more the field is induced by the circulating electrons shielding the nucleus, the higher must be the applied field to achieve resonance. If the field is more, applied field also should be more to obtain the resonance. So, the value of the shielding constant depends on several factors, among which are hybridization and electronegativity of the groups attached to the atom to which the nucleus belongs. The shielding effects rarely extends beyond one bond length. That means, if you have a long molecule, the shielding effect a particular proton experiences does not experience, it will experience only the from the carbon atoms and the environment to the next carbon atoms and not next to next or something like that. So, to express the position of the resonances independent of the strength of the applied field, the resonance of a reference compound is required. For proton spectra and non-aqueous media, the reference is tetramethylsilane. So, this does not have any hydrogen groups. TMS gives a single sharp signal due to 12 equivalent protons, and this is taken as 0.0 on the chemical shift scale. That means, you take the spectra of tetramethylsilane, apply it, say this is the 0, from this is the reference material from which we measure the different chemical shifts. So, the magnitude of the chemical shift is expressed as simple equation like this, that is delta is equal to reference minus H sample by H reference multiplied by 10 raised to 6, that is for the applied field, and which can be converted, which is almost equivalent to V reference, V sample, and multiplied by 10 raised to 6. So, a positive delta shift represents greater degree of shielding than the reference. If it comes on the right side, then we know that it is a longer the positive shift. So, for other nuclei, the recommended reference materials are carbon disulfide for C13, carbon CCl3F for 19F, and ammonia you can use it for 14N and 15 nitrogen. TMS is for 29 silicon and 85% orthophosphoric acid for phosphorus. You can see that most of the reference materials contain fluoride, 19F it is, there has to be one fluorine, for nitrogen there has to be nitrogen, silicon is silicon, and for phosphorus it has to be orthophosphoric acid. These are the reference materials. So, proton references from CH bonds are found in the range delta is equal to 0.9 to 1.5 when aliphatic groups are the substituents. So, now we are talking about the chemical shifts where the peaks may appear. So, from tetramethylsilane the shift should be 0.9 to 1.5. For methyl protons, they generally show up slightly down the field in that order. If there is an adjacent unsaturated bond, the proton shifts will you will be observing slightly higher than this 1.5, but in the range of 1.6 to 2.7 range. So, and suppose there is an adjacent oxygen atom like OH group, then this shifts the proton signal downfield almost 3.2 to 3.4 for aliphatic entities, and for 3.6 to 3.9 for aryl groups, that is aryl oxygen and CH entities, C6H5OCH3 something like that. You would be seeing the chemical shifts of the order of about 3.6 to 3.9. Suppose there is a double bond or triple bond present in the molecule, the electrons in these bonds can circulate only in particular directions. A double bond is always parallel to the main axis. So, but the actual electronic orientation is perpendicular to that. So, this figure shows shielding and de-shielding zones in the neighborhood of triple bond, double bond and single bond. Just look at this figure. So, here you can see this is the triple bond and this is the double bond. This shielding effect is like this, and this is minus, this is plus, and this is plus. This is for aromatic compounds. Induced magnetic fields have got to be above the basic ring structure and below the basic ring structure. So, the electrons have got to be moving around it like this. Similarly, on the other side also. So, in carbon carbon double bond and carbon oxygen double bond, suppose there you are handling different compounds, the de-shielding zone extends along the bond direction. The carbon bonds also show this some amount of de-shielding in this direction, that is single bonds. The de-shielding of a proton depends upon the latter's distance from the bond and also on its orientation with respect to that bond. Alternative aromatic ring structures have a strong anisotropic field effect, and the delocalized pi electrons of an aromatic ring circulate in a two donut shaped orbits on each side of the ring, just like just now I have shown you this donut shaped ring. So, the circulation results in a magnetic field that opposes the applied magnetic field in a cone shaped region of excess shielding that extends along the particular along the perpendicular to the ring plane, but reinforces H 0 in a zone of de-shielding from the edge of the ring. Thus, in aromatic compounds, protons which are usually found in the de-shielding zone appear at much lower fields. Approximately delta chemical shift should be between 6 and 7. Then the olefinic electrons, where olefinic electrons will show you the shift between 5 and 6. So, in acetylenes it has to be still less. The electron current circulates in such a way that the shielding zone extends along the bond direction, and the acetylenic protons appear at still higher fields, approximately 1.6 to 3.0. Now, you would see that I have listed here some of the chemical shift of some compounds, that is HCCl, that is carbon chlorine and this hydrogen, where you would see if it is methyl you would see 3.05, and if it is methylene protons it is around 3.45. If it is methine protons like in acetylenic groups, the shift would be around 4.05. Similarly, databases are available for different types of compounds. For example, the second one is HCOH instead of chlorine or OR. Here you would see the numbers like 3.20 for methyl, 3.40 for methylene and 3.60 for methane groups. So, suppose you have a cyclopropane group, all of them are approximately equivalent, but if the substituents are methylene protons, then the chemical shift would be hardly 0.20 and this would be around 0.40. I suggest you study all these chemical shifts to get an idea of about how these chemical shifts are manipulated and then interpreted. This I have taken it from J. A. Dean, Lange's Handbook of Chemistry, 13th edition. It is available. Similarly, I have put the data for chemical shifts of some compounds like alkanes and then halides, alkynes, alkenes, etc. Here in this case it is primary carbon, secondary carbon, tertiary carbon and quaternary carbon, and substituent groups will show the delta chemical shifts in this range, and it is a good idea to study the effect of functional groups on the shifts. Now, let us discuss about the spin-spin coupling. Nuclei in proximity with each other causing a splitting of resonance lines into multiplets. So, this I have shown you a figure of C2H5I. This is called as spin-spin coupling or J coupling. This is due to the interaction of magnetic moments of the nuclei through the magnetic properties of the electrons in the intervening bonds. The strength of the coupling is denoted by J, which is equal to the spacing of the multiplets in hertz. So, the proton-proton couplings in aliphatic organic compounds are normally transmitted through only 2 or 3 bonds. So, the proton spin coupling also I have put it in the small table. You can go through this and study the proton-proton spin coupling. In the double bond spectrums, double bond straight chain systems, coupling can be observed over several bond strengths. In aromatic rings, coupling of protons in ortho positions, you can calculate from the table, you can see that they are around 7 to 9 hertz, and for meta it is 2 to 3, and for para positions it is 0.5 to 1. That means, depending upon the chemical shifts, you can find out whether a particular substituent is in ortho, meta or para. So, coupling also depends further on the geometry. So, axial protons are strongly coupled, but axial equatorial and equatorial protons are coupled moderately. It has been shown that the J translation and J isomer is approximately 2. The number of lines in a multiplet is always given by 2n plus 1 lines. So, in a multiplet, the total intensity also varies according to the proportional to the number of nuclei involved, and the individual peaks follow the coefficients of binomial expansion. For example, one neighboring proton splits the observed resonance into a doublet, and 2 will produce a triplet of 1:2:1 ratio, 3 would be a quartet with 1:3:3:1, and 4 would be a quintet with 1, 4, 6 and 4, 1, etc. So, the magnitude of the J is independent of the field strength, but other nuclei with spin half etc., that is 19F and 31P interact with protons and cause spin-spin splitting. So, when a proton is coupled to a nucleus that has a quadrupole moment, spin lattice relaxation becomes so efficient that the spin-spin interaction becomes with proton is greatly or completely decoupled. Coupling of protons with chlorine, bromine, iodine is etc. is therefore not observed. So, we will continue our discussion. There are hardly about 3 or 4 figures, slides in which I want to convey the remaining information, and then we will move on to the electrometric techniques.